Okay, doing the next problem, number 68. We're given an air-filled capacitor connected to a battery. And we have a charge on it before we drop the battery in. It's 150 microcoulombs. Before we drop the dielectric in. Once we drop the dielectric in, the charge changes to 350 microcoulombs, right? So I didn't draw the diagram here, but I can do that quickly. So we have a battery, and these are parallel plate capacitors here, and then we're going to drop a dielectric in, and that changes the overall charge from Q naught to Q when we do that, okay? So we're asked to find the dielectric constant. And I did go through and find this is actually an equation in the book that is very useful. So to find the dielectric constant, we can just take the capacitance, the ratio of capacitances, right, the final over the initial, and we'll find the constant. So that's pretty easy. That's really straightforward, right? So the initial is going to be Q initial over delta V, right? Let me just check. Okay, now, so then we have next final is going to be Q final over delta V. So what we want, this is going to stay the same, because what we know is that capacitance is changing in both scenarios. We know that the charge is changing in both scenarios. So we need some constant in these to make sure that our system follows our laws, right? So delta V is going to stay the same. So in this case, when we take C over CF over CO, C naught, we're going to get QF over delta V over Q initial, right? So those cancel, and then we're just left with the ratio of charges. That's going to be 350 microcoulombs over 150 microcoulombs. These units cancel, and we're left with approximately 2.33. That's our dielectric constant for this scenario.